Welcome. So this is a new module about field method where we will try to apply or bring together what we have learned before, and by the end of this module you will be able to develop a conceptual site model for a groundwater that you will later use this conceptual site model to develop a groundwater flow model and use it for different engineering applications. Okay, so just let's start. This is things that you learn in surface hydrology. This is things that you learn in groundwater hydrology. So we did already aquifers, groundwater flow, well hydraulics, and we will bring like what we learned from well hydraulics, which is how to estimate hydraulic conductivity, and we will bring what we learned from aquifers, which is uh, hydraulic conductivity and how to characterize hydraulic conductivity and different hydraulic conductivity zone. We will bring these two together to, and also what we learned from groundwater flow about surface water, groundwater interactions and boundary condition and things like that. We will bring all these information to develop a conceptual a conceptual a conceptual model for groundwater flow. Okay. Uh, so let's get started. So if you like for some of the methods that we will be covering in this module, if you want to study them in depth, here are three books, recommended books. So this one, electrical imaging for hydrogeology, and in this one you will learn more, like if you want, like we will cover electrical imaging, and if you want to learn more about like electrical imaging, you can check this book. This book is about geophysical logging, so we will learn about like geophysics. So there is surface geophysics, like electrical imaging, like not electrical imaging, because electrical imaging can be surface and boreholes. There is surface geophysics, something you can do on the surface. So let's say here is your surface. Yeah. Oops. Let's say this is your surface, and then like you put your instrument here and you measure, like let's say you measure what's down here. Yeah. There's also borehole geophysics. So that's like this book. Borehole geophysics is that like you have your borehole and then you put your instrument here. Like you put like your instrument and then you measure something along here. Yeah. So you measure here. Surface geophysics, you put it on the surface, it's non-intrusive, and then you measure downstairs. So that book is about like this surface geophysics. There's many different hydrogeophysical method for to do like this surface geophysics. Electrical resistivity, that's one of them, but there is also seismic, there is also gravitational methods, there is also uh, magnetic. So there are like many of them, yeah. And I did like I did seismic before. I did magnetic to lunar before. That's remember when I told you I did some field work in Hawaii up to the Mauna Loa Mountains. That was magnetic to lunar, like some magnetic methods. And I did electrical geophysics also. And that's different way to characterize the subsurface to get like different information about the subsurface. And I did also borehole geophysics. That's what I did a lot, and we will talk a lot also about this. So in this lesson, we will talk about like surface geophysics and borehole geophysics. And then in lesson two of this module, I will show you how you could bring data from geophysics, mainly like surface geophysics, along with pumping test data to create a conceptual model for your subsurface. Yeah, to create like a conceptual model. Like I mean, This is not really conceptual. Like this looks more like, I think, I can't read. I don't know what sense this figure is unclear. But to create like a conceptual geological model for your subsurface, which you can later use in for groundwater flow modeling. Yeah, and to learn more about like geological framework for groundwater flow model, you can also check this book. Also, your other textbook is a fitter one. It has one chapter about the field method you can also check, but it's just brief, like wouldn't be as more. But it's a good introduction. Yeah, if you want to read more, I think you can also check fitter book. And I think it's chapter 9, if, or I don't know. I have to check. I don't remember the chapter number, but this is one chapter about field method. But anyway, let's get started. Yeah. So this is our first lesson here in this module, which is electrical resistivity imaging. And this is one of the commonly used hydrogeophysics method. It's commonly used because it's easy to use it, yeah, and it is not expensive and not labor intensive as would be other method, yeah. Uh, I did this, for example, when I was doing this field work in Ireland. We did electrical resistivity. The reason we did electrical resistivity, we wanted to drill some boreholes, monitoring boreholes, two monitoring boreholes, and then we did this electrical resistivity to identify where to drill this borehole, because in Ireland it's a car system similar to here to Florida, but here in Florida, the car system is like kind of fluffy and wet. In Ireland, it is hard and dry. So you just drill and it's dry. You drill and it's dry. You drill and it's dry. So we wanted to identify like areas where water is flowing, and we also wanted to identify area karst feature like caves or something like this, so that the driller will not lose his drill bit while he's drilling. Yeah. So we wanted to identify like a water pairing like layer, and identify also caves and things like that uh, for practical reasons. Yeah. And so that was the objective of this analysis, and it was very successful. Like that helped us to identify like our success rate. Like usually when they drill there, they could drill, keep drilling, and it's dry, dry, dry. So like a lot of the boreholes that was drilled there was already dry. But in our case, the success rate was like we drilled two boreholes, both of them were not dry, and even one of them we found two water pairing layers. So it's like the success rate was almost over 100. Yeah. But anyway, so let's get started. So by the end of this lesson, you should be able to describe the basic principle of electrical resistivity imaging for aquifer investigation. Yeah, so that's by the end of this lesson, you should be able to do this. Yeah, and there is also like a field trip information would be about this field trip is on Canvas. In this field trip, you will conduct like this electrical resistivity imaging. So, and that would be part of it, or could be part of it. And information about like this field trip would be on Canvas. Okay, so that's like your social media activity for this module. Uh, and okay, let's just get started. Yeah, it's long introduction, like it's a almost 10-minute introduction. So electrical resistivity imaging, it's a very simple principle. It's based on something you already learned in physics. I don't know if you still remember it. Probably you do, because you learned it also at school. Like V is equal to IR. Like, do you remember this? Yeah. So there is a current, there is a potential, and there is resistance. That's it. Yeah. So, and that's basically all what this method is. Yeah, you transmit a current. So like you have an equipment. With this equipment, you transmit a current. Yeah. So here, let's say here, transmit current A and B. Where's A and B? So here is A and B. So I transmit a current. Yeah, here. So like you see, I transmit a current here, and then this current, what will happen? It will pass like through the ground, yeah. And then what I do here, I measure voltage. So like see, so I have two electrode A and electrode B for sending a current, like creating this circuit. And I have like two electrode M and electrode N for measuring voltage. So, and that's it. Yeah. So if I know the current, like I know the currents that I'm sending, I can measure so this is known, yeah, because I'm sending this current. uh, I can record the voltage that I'm receiving, then I could infer resistance in between. Then that's how you infer the resistance of this earth material. And different earth material will have different resistance, or we call it, we don't call it like resistance, we call it resistivity, because resistance, this is resistivity, that's a property of a material, yeah. And so resistance has the unit of like ohm, yeah. Resistivity has ohm meters as a unit of resistivity. So basically you measure resistance and you convert it, like you get it like in unit of like resistivity. Okay, so that's it, yeah. So it's very simple principle, yeah. I send current, I measure voltage, and then I can calculate like a resistivity in between. That's like in a nutshell like this idea. So the instrument looks something like this. So here, see these yellow things here? These are these electrodes, yeah? So so that would be like, see this yellow thing here? That would be like here, 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 yeah? That's like these electrodes. See this cord here is to connect like these electrodes together. So like you see, you connect this one to this one to this one, like so you connect this together. This is like a battery, for example, and this is the instrument where like it will send the current and will measure the electrodes. So basically, you connect this core to this electrode and you connect it to your ERT instrument. And you need, of course, like a battery source and like a good battery source, because that could drain like a car battery. Like if you're doing this for 1 day, that could drain like a full car battery, for example. Yeah. Uh, Now, how you arrange your electrode, so you can arrange like this is one configuration for how you arrange your electrode, but your electrode could be arranged in different ways. So this way, like this image that you see here, this would be Schlumberger. So here, like A, the distance from M to N is A, and here NA from A to M, or N to A. This is called Werner Wessed, like where A, they're all equal, like you put them all at an equal spacing. You can do ball dipole, you can do pole pole, you can do dipole dipole, you can do like gradient. So there are different configuration, and these different configuration, like the details of these different configuration are not important for this lesson. But before, like with each instrument you will get, it will have a manual and it will show you like what this instrument can do. Because you lay out your electrode and then your instrument, because you generally don't lay full electrode. Like the instrument we have, each of these line has like, you can lay 12 electrodes. So the instrument we have, we can lay like 48 of these guys. So you lay this 48 guys, and then within your instrument can tell you, okay, like if depending on the purpose of the analysis, how deep it is or how shallow it is, the type of the materials that you are expecting in your subsurface, you can select like which of these electrode configurations instrument will use. Yeah. So so that is something that, like, once you start doing it, you read the manual and see which would better suit your investigation. And I have a video that's coming later. I will show you like where you can learn more about this for the instruments that we have, for example. Yeah. Because here I don't want to, in this video I just want to cover the main concept. That's the most important thing, is that like you understand the main concept, and then the implementation details. That's like you read this in the manual before you do it. And it's very simple, but let's focus on the main concept here. Yeah. So the main concept, as I told you, is that like resistance, like here, uh, V equal to IR. Yeah. Resistance R is not a fundamental physical property of the material, but resistivity, this is a fundamental physical property of the material. Yeah. And resistivity, that is it has the unit of ohm meter. Yeah, so like resistant has the unit of ohm, resistivity has the unit of ohm meter, uh, and it is like resistivity. Let me show you, like, so resistivity is generally like resistance time area over length. Yeah. So that's like so like resistant has the unit of ohm, area, let's say like L square, and this is L, so you get like L, or let's just write it in meter, like meter square over M, so you get like ohm meter. Yeah. So that is the area, uh, like, so that's like the length over like your cross section area where like the current is passing, and then you get like this ohm meter, and this is different, uh, different. Uh, Materials will have different resistivity. So, for example, sand and gravel, they have high electrical resistivity. Sand and gravel has high hydraulic conductivity. So that could be confusing to some student because like uh, so sand, yeah, sand, yeah, and gravel, they have high hydraulic conductivity, but they have low electrical resistivity. So they have low electrical resistivity, like rho is an ohm meter. Yeah. So they have high hydraulic conductivity. Hydraulic conductivity is as uh, like let's say meter per day. Yeah, whatever. Yeah, meter per day. Yeah. This high hydraulic conductivity by low electrical resistivity. Clay, for example, has a low hydraulic conductivity but high electrical resistivity. And that's what you see here. So like you see like here clay, this is the resistivity ohm meter. So here very, it's on a log scale, and this is a very high resistivity. So you see here like the sand, it has low hydraulic conductivity, low hydraulic conductivity, but sorry, I, sorry, like I made a mistake here. Clay has like low resistivity. I mean, like clay, it has low resistivity, which means it has high like high electrical conductivity, but low clay has high electrical conductivity. High electrical conductivity means what? Means low resistivity, and it has low hydraulic conductivity. Okay, I mean, does this make sense? Because if it's high electrical conductivity means that it has low resistivity. That's exactly what is here. So clay, it has like low resistivity because it has high electrical conductivity. So it has like a high electrical conductivity but low hydraulic conductivity. That's the confusing part. So I even got confused myself. Yeah. Okay. So is this clear? Yeah. So clay, it has like low hydraulic conductivity and low resistivity, which means like high electrical conductivity. Yeah. And why clay has like a high electrical conductivity? Because it has a lot of charged particle. So clay, remember when we talked about clay, it has all this like negatively charged particle, and that's why it is a good conductor for electricity. It's like low, it has low resistivity, low electrical resistivity versus sand and gravel. Sand and gravel, they are silica. So silica, they don't have any charged particles, so they don't conduct electricity. Sand is a not good conductor for electricity. So it has a high electrical resistivity. That's the idea. Yeah, sand is not a good conductor for electricity versus clay. It is a good conductor for electricity. And you see here like different uh, units, like different geological unit will have different electrical resistivity, and that's how we interpret this image. Like you take an image of the subsurface, let's say we are at Immokalee, yeah, and at Immokalee we are expecting to find like mainly sand and gravel and maybe some clay layers, yeah. So you do like your resistivity test, and then you will find like areas with low K, yeah, and areas with sorry, low like resistivity, low like low resistivity, and area with like high resistivity. And then when you look at these images, then you'll say, oh, okay, this is like an area of low resistivity, and this is an area of high resistivity. So this means that could be, I could interpret this as sand and gravel, and I could interpret this as clay, for example. Yeah. Let's look at limestone. So where is limestone here? So these are metamorphic rock. These are igneous rock. This is like a, shale, like see limestone here. Uh, so limestone here, it has like a very high electric resistivity. So now, if you are in Immokalee, again, you can use this information because you will like limestone has a very high resistivity. So that basically will be like your bedrock. And then above the limestone, you could find like some gravel and sand. So the gravel and sand, the resistivity of the gravel and sand would be less, and then you will find like clay. And that's how you'll be able to identify where your bedrock start, for example. And then above the bedrock, this sedimentary area, you will be able to see where are the like gravel lenses and gravel and sand lenses, and where are the clay lenses, yeah, in this unit. Okay, so that's basically how you do it. Now, another thing you can also identify from this is salt water and fresh water, because salt water is very good, is more conductive than fresh water. Yeah. So salt water, you have like sodium chloride, charged particles, so they conduct salt water conduct electricity better than fresh water. So you see orders of magnitude between the resistivity of salt water here, very low resistivity, and here much higher resistivity for. So that's like salt water, fresh water, and like permafrost, and that's like sea ice in between. So you can also identify this is for water or fluid, and this is for different like rocks. Yeah. uh, okay, and then again, before you do also this test, you should understand your subsurface geology, what you are expecting. Like, am I expecting to get limestone? Am I expecting to get like sand and clay? Am I expecting to get like igneous or metamorphic rock? Or am I expecting to, you should have like an understanding of what you are expecting, like sandstone, for example. Okay, cool. Like this is cool, like lignite, dolomite, and this is like limestone. Uh, but what is like? Let me ask you a question. Like, what is like? Do we only do this like to understand the subsurface? Because remember, this is just a method to know. Like, this is like when you go to a doctor. Let's say you have like a broken bone. Like, what do? Like, you go to the doctor, and the doctor will make like an X-ray, and then X-ray he will see what's below the skin and say, oh, you have a fracture here. This is similar. Like, we are doing kind of imaging for the subsurface, yeah. And so do we do this imaging for the subsurface for only water resources application, or like, or this is would be commonly used in other civil and environmental engineering application? So maybe pause the video and think about this. Like, if you think about this, like find like, how about this? Like, find two application, yeah, for like if you are a water resources engineer, not necessarily groundwater, just like water resources, yeah, including groundwater, yeah, because that's part of water resource. If you are water resources engineer, what would be two application for something like this one, like electrical resistivity? If you are an environmental engineer, what would be two application for something like environmental resistivity? Learning about your subsurface and different formation in the subsurface. If you are a structural or geotechnical engineer, and if you are like a transportation engineer, yeah. So just pause the video and think about two applications for each, and then we can discuss. Yeah. Okay, so welcome back. For me, like I like two water resources applications that I identified. I already mentioned one, which is locate and map groundwater resources by identifying potential water pairing formation and estimate like the thickness and extent of each. So that is one application similar to what I did in Ireland. And we will I will show you some example like later, yeah. So if you I will show you later some example. Uh, as water resources engineer, it could be also to identify like weakness or seepage pathway to evaluate integrity of a dam or a levees or something like this. Like you have your hydraulic structure and then you want to know where the bedrock is, or if you want to identify some feature like sinkhole or things like that, that could impact like the integrity of your hydraulic structure. So that would be, or potential seepage, like potential seepage, like sand unit or gravel, sand and gravel units, or potential like areas of clay, like impervious layers that could also impact the integrity of your hydraulic structure. Environmental engineering, it could also be used to map like contaminant plume, like monitoring leachate in landfill site, because leachate, it will like as a liquid, it will have a different hydraulic conductivity, different, sorry, resistivity, electrical resistivity value than nearby fluid. So you can monitor like leachate, for example, in landfill site. So that's like one application. Another application is to characterize the subsurface, to do like your remediation, like to develop a groundwater model and to design your remediation system, as I showed you in the very first video, where we needed to identify like different hydraulic conductivity zone. Like to do this, you need to do like one of these imaging methods. And we will talk about this later when we come to modeling. I will get back to this case study now after the knowledge you've gained, and I will show you like how to identify like a different hydraulic conductivity zone. And then you will also do this in this module. So the objective by the end of this module, you should be able to do this, yeah, like use this data from electrical resistivity to make like a hydraulic, to construct the hydraulic conductivity field of your subsurface. Another thing in environmental engineering is also a very important thing, is pipeline and utility detection. Sometimes when you are working, especially in historic and old cities, is blueprints or the maps for the existing utilities, they are not known. Like if you go to the utility municipalities and you tell them, okay, where should we expect to find like some water pipe or things like that, they don't know, yeah. Or this map doesn't exist, and you don't want to like do some excavation and damage like these utilities, this pipeline or utility detection. So water and gas like pipeline, electrical conduit, sewer pipeline, so to prevent accidental damage during excavation, then you can conduct this electrical resistivity method to identify this feature, because this feature will appear. They will have an anomaly with surrounding material. Yeah, so that would be like an environmental engineering. In structure and geotechnical engineering, that's a lot of application. Like you want to identify like the depths and thickness of different like geological layer. Like this is soil, this is like my aquifer or clay lenses are here, and here is my bedrock. So that's very important to design your foundation. So like let's say you are doing piles, so you generally need to put this pile on the in this bedrock. So you do this electrical resistivity image to identify like where your bedrock is. And then you can also do this to identify different material to assess rock properties like the bearing capacities, the shear strength for the design of your foundation. So the bearing capacity for clay would be different than gravel than it's for sand, for example. Yeah. Uh, you also want to assess subsurface condition for some site choice, like if you are doing some subsurface structure like a tunnel, for example. So you want to assess the subsurface condition to say, okay, where would I put this tunnel? So that would be like a transportation engineering application. Yeah. Another transportation engineering application would be detect like sinkhole to assess risk for infrastructure. You want to build the road and you don't want to build this road like a major highway where there is a sinkhole under it. So you do this electrical resistivity imaging, for example, to identify or other geophysical method, not necessarily electrical resistivity, but electrical resistivity could also help to detect like sinkhole. Yeah. Similarly, you can do this to identify like faults, like in the subsurface. And faults are very important if you are worried about seismic activity. So for vulnerable structure and you are that are susceptible to seismic activity, you don't want to be messing up with an existing fault because you can liquefy this fault and then you create a seismic activity. Yeah. So that's all like so that's another application for this method is to identify faults also in the subsurface. Okay. So you see it's they are very useful and whether you are like in working in a construction site or whether you are working in engineering like in design, uh, both like you would need this information. Yeah, whether for construction, before construction, or during the design phase. You usually get this type of information as usually part of your design. Okay, so let's learn now. So that was just like an overview about this method, and let's see an example. Yeah. So let's just see an example, and there are different. I remember I told you there are different type of imaging. So one type of imaging is called like profiling. Yeah. So this is one type of imaging. So profiling is simple. Uh, let's say this is here, like this is so you send this current here. Yeah. So let's say like I'm sending this current. Yeah. And I'm measuring the voltage here. Okay. So that's, let's say I'm just conducting this with only 4 electrodes. Like I told you, the instrument we have has 48 electrodes. Usually, like you have many of them. Uh, that will save you time. So the more electrode you have, the more time you will save. So, but let's just do it simple, like just 4 electrode, two to send current and two to receive. And then you just keep like this is your subsurface. So profiling will basically go like over like you will send current in this distance and receive it here, then you will just see okay what is the you will get an average resistivity value for this one. Yeah. And then you move your electrode. Yeah. So like so here like you got an average resistivity value for this one, like here this is like your bedrock. Mainly it will cover mainly like your, let me change the color, it's better to change the color. Me where to change the color. Here we go. Oops. Let me just change the color. Ben color. Let me do this one. Okay. Okay. Here we go. And let's start here. Okay. So I'm measuring the resistivity in this region. Yeah. So it would be somewhere here. Yeah. So that include what? So that like if you see here, this is like so let's assume that we know the subsurface. Yeah. So once we know the subsurface, oops, I think I have a problem here. This card, I think this got shifted. Sorry about this. This got shifted. This is here. Okay, here we go. It's here. That's good. This is good here. The rest is good. So let's say I already know my subsurface, yeah? Maybe a little bit. It's also got shifted a little bit. Okay. So here, this is sand, yeah? And this is sand, and this is clay. So we expect, like just before we do any resistivity, like we expect what? Here, this is clay, yeah? So we expect that resistivity would be low here. It would be high here because sand is a poor conductor for electricity. It has high resistivity. It would be high here and it would be low here. And it would be low here. So if I will draw like a resistivity profile, it will be like low, 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 and then it will be high here, and then it would be low here, and then it will be high here, and then high. So this is this one, this is this one, this is this one. So that's basically what I will expect. And if I measure this, so like I am at the surface, yeah, and this is what I'm measuring. So like I start like measuring this here. So I will expect to get a low value here. Then let's say then I moved here, yeah. So if I moved here, now I'm measuring here. Oops. So if I'm measuring here, I'm also expecting to get like another low value here. Yeah, so that's what I got, like another low value here. Oops. And then I moved here. Here I'm starting to get to measure this sand. So this is low resistivity, this is high resistivity. So I might get something here. Yeah, that's what be my expectation. Yeah. Here I'm moving more toward sand. Like, see, I'm like my sample here is more sand and less clay. So the resistivity should be somewhere here. Yeah. Yeah. See, I'm getting here. Here is more sand. So maybe I get something here. Yeah. And so on. Like, see, and so on. Now here I'm moving to the clay layer. So I get like low resistivity. Like here, most of what I'm measuring here is in this sand area. So I get like this resistivity and I move so on and so forth until I get back to my bedrock. So my resistivity profile would look something like this. And then how would I interpret this? I would interpret this as clay, sand. Yeah, you see here, this is the sand. Clay, sand, and clay. Yeah, that's how I will interpret it, like as this resistivity profile. Now, you might tell me at what depth you are measuring this. So that's exactly how the depth will be determined by how you place this electrode. So if you want to get like a more depth, you will put them at a larger distance. If you want to get shallow depths, you put them at a smaller distance. So if I want to get this like at a shallow depth, you get it at a large, like you put it at smaller distance. If I want to go deeper, like if I, let's say if I put this here and this here, then no, I will just go deeper. Yeah, I will be going deeper. Versus if I put this like A, if I put like A here and I put B here, then I will be going shallower. Yeah, so that's, and then like this value we get is like a depth average. Yeah, so like this value we get is like an average, like this value here, it is the average of the resistivity in this region. Like this value here could be like the average of resistivity in this region. This value here is the average of resistivity in this region. Yeah, this value here, it is the average of resistivity, let's say in this region. But some of you might say, okay, but what if I want to see how resistivity is changing with depth? Like I don't want to see like the average resistivity over this or over here, but I want to see how resistivity is changing with depth. So if you want to see how resistivity is changing with depth, that's not going to be called profiling. That will be called like sounding. So that is our, so here, like just to sum up what we did, sand and gravel pervious, like where water is good conductor for water, high electrical resistivity and high hydraulic conductivity. Yeah. sorry. Yeah, high electrical resistivity. Yeah, you see the resistivity is very high, high electrical resistivity, and high hydraulic conductivity. Clay, silt, and shale, like impervious material where water does not flow. Low electrical resistivity, you see the electrical resistivity is low, and low hydraulic conductivity. That's the main lessons that I want you to understand from all this. So I've been talking for, I don't know, half an hour or something more than half an hour, like 40 minutes now, just to tell you this. Okay. Now, this is profiling, but let's say some of you will say, oh, I don't want to know this. I just want to see, like, I know tilt has a low resistivity. Yeah. Like here, like tilt, this tilt will has a low resistivity. Then this sand will has high resistivity. And then this bedrock will has low resistivity. So if I want to see this profile, then this is, if I want to see this uh, like this vertically change in resistivity. Then this is not called profiling, this is called like sounding. So here is an example. So this is the sounding, and remember I told you, like if I want to go deeper, what do? I just make this like further apart. So that's exactly how you do it. Like you place this at like small distance, and then when you place it at small distance, you are measuring basically resistivity here. Yeah. And then you make it further apart. Like you make it further apart, then you'll be measuring resistivity here. Then you make it further apart. And when you make it further apart, you'll be measuring resistivity here. And so on and so forth. And that's how you do like sounding. So if I did this sounding, so at like here at this one, I'm measuring resistivity here, and this is still, this has low resistivity. So I should get something here like low resistivity. Yeah. So I got like this point here. And then like now here, I'm measuring like resistivity here. That should be like slightly higher. Yeah. And then here I'm measuring, oops, I'm measuring like resistivity in this region, maybe something like this. Then that should be like the resistivity should be slightly higher because this is sand. Yeah, still is like a good conductor for electricity, similar to clay. Sand is not a good conductor for electricity. So I got something here. Then if I go further, see now I'm measuring like at this depth here. Yeah, so if I got like further, and then if I go even further, I will be like, if I got even further, then I would be measuring at this depth here. It's in this borehole. Yeah. So that's like this one is called like sounding. Yeah. So the previous one is called profiling. Like I'm getting this profile. So this profile would look something like this: low electrical resistivity, high electrical resistivity, low electrical resistivity, high electrical resistivity, low electrical resistivity. And this is profiling. So this is profiling. Sounding, if I just want to at this point, then the sounding here would look like this: low electrical resistivity, high electrical resistivity, and low electrical resistivity. Can I bring these two pieces of information together? Yes, and this is called like tomography, electrical resistivity tomography, ERT. Basically, electrical resistivity tomography, you just build like these 2D image, this 2D transect from by doing profiling and sounding, and that's what I told you. Remember, I told you we usually do this like you don't only use full electrode like the instrument we have like you that you will see in the field trip. It has like 48 electrodes. Yeah, it has four cords. Each cord has 12 electrode. You can hook up 12 electrode to it, and then you can hook those 48 electrode to the machine. And then like you see here in this transect, uh, so that would be like you go, you make your measurement, and then after you make your measurements, there is a software you do like inversion to convert resistance to resistivity. So that's done by software. It will convert like based on your distances and all these things. It will convert like this to like your resistivity value. And now here this is like your resistivity value. So you see here, this is low resistivity, and this is like high resistivity. So that would be like clay, that would be sandy clay, that would be clayed sand, that would be silty sand, and that would be cemented sand, which would have like the highest hydraulic conductivity. And that's basically, so I have clay here, I have clay here, I have clay here, I have clay here. So like if you interpret this, that's where your clay are. So does this sound familiar? Yeah, that's like your confining unit. So here you have a confining unit here. Okay. And this is with depth. So the depth goes from this is in feet, like 30 feet to negative 60 feet. So that's about like what, like 100 feet. So you're going deep 100 feet. So you have like your confining layer here, and then you have your aquifer here. But then even this aquifer, it is heterogeneous. You can now see the heterogeneity. Like you have some cemented sand here. This is high conductivity. This is high conductivity, and this is high conductivity. Yeah. And remember when we talked about, and this is the distance in feet, so that's like 500 feet. So now if you want to conduct a pumping test, for example, like before you conduct a pumping test, if you have an image like this will show you what would be the best place to conduct your pumping test. Like, so this would be like, here's this area, like, so you have silty sand or sand, and so that might be like, that's not really a very good aquifer because it's mostly clay sand and silty sand or sand. So it's most of it like it's only you have only this. So basically, you might say that this is not a good place to best place for your production well because it's mostly clay. Like you have a lot of clay here and some clay here. But for your other engineering applications that we discussed, that could has implication, like implication on like you know the soil for like designing your foundation, for example. Or here, for example, like this is better, like this is like cemented sand. So you have a lot of sand here, you have a lot of sand here, like and some clay here and a lot of sand. So that might be, so that would be like another image, like a transect, another transect. Okay. So this is the instrument that we have here at engineering. So if you go here, I'm not gonna like, if you go here, you will find like some details about the instrument and how like groundwater prospecting, geological mapping, mineral exploration. You can see like how you can apply this instrument. This is the results that you get out of the instruments. You can check this here. Now, this is, remember I told you if you want to learn this configuration here, like which configuration to use, like Werner, oops, for example, or Schlumberger or dipole or gradient, that would depend on the depths that you're interested in, the materials that you're interested in, and the purpose of the study. And if you want to learn these details, uh, where to learn these details. If you want to learn these details, here you can check like this YouTube videos. Oops, it's a half day training. This video is like 3 hours. It will include like this detail. It will also include background information about like this more background information beyond like this short lesson about this electrical resistivity surveying. And then this 1 hour video is about like the data analysis, like once you go to the field after you finish your survey and how to do data, like get your data, process your data, and do data inversion. And also you can check here, check this is the surface water, groundwater field labs that we have here at FGCU, and you can also read what other instrument is that we have. So this is, for example, an auto sampler. This is a sonde for water quality. This is a pump here. This is a weather station. This is soil moisture sensors. Uh, this is the Satur where for measuring hydraulic conductivity, saturated hydraulic conductivity at the field, this infiltrometer. This is a logger for these sensors, for example. This is a water dipper. Remember the water dipper for measuring water level. So this is called like water level meter. This is a flow meter, and here this is this equipment like this hydrogeophysics, electrical resistivity, and these are some other field equipment. So if you want to use this for your project, remember like there is a project you can do. If you want to do like independent learning and do your own project, you can do this, or you can just do the project that I will provide to you in this class. Yeah. So if you want to do your own project, these are the field instruments that we have here at FGCU. This is an auto sampler. So auto sampler It basically like you configure it and then it will take sample every 1 hour or every 2 hour or whatever as you configure it. So that's like if you're doing a tracer test. So when we were doing a tracer test, for example, like we use this auto sampler to connect sample at regular intervals, and you get your sample and then you analyze them. Yeah. We had like this sonode, like so we had this node and there was like we had like several of these, like we did this field work with FSU. For example, they had like their node has those rhythm sensor, and that they got this for dye tracing. So they were doing dye tracing and then they will like monitoring the dye with those rhythm sensor, for example. Yeah. Okay. So this is like what we did, like this three method, like is a ERT or its component like sounding and profiling. Yeah, this component like profiling or sounding. This is called like surface geophysics. Now, another type of geophysics is called like borehole geophysics or well logging. Yeah, so ERT, that's something you do on the surface. This is well logging. So well logging, that is something you do typically, like, so that's for example, when I was doing field work in Ireland, we get like a driller to drill this borehole. I think it was 50-meter deep. And then after you drill this borehole, what the driller will do as like give you as like a bonus, or like give you as something extra, because this drilling is very expensive. I think each borehole was about 20,000 euro or something. I don't remember the exact number, but it was something like this. So what he will the driller will give you two things. The first thing he will give you is the drilling log. So that's the drilling log. Yeah. So that's the drilling log. So the drilling log, he will tell you, as I was drilling, I found like from this depth to this depth, I found sand. Because as he's drilling, he is you can the material will be coming out. He's drilling out the material, so you can hold it and see what it is. Sometimes there are two types of drilling. There is like regular drilling, and uh, there is coring. Coring is that like you get the core exactly intact. So you try to drill in a way that you get the core out intact, like the geological core intact. But we don't generally do coring for unless you have like specific purpose for it, because it is like two or three or even four times more expensive than just regular drilling. Yeah. So regular drilling, you have like an auger, it will go down and bring the material out. Yeah. Coring, you drill in a certain way that you get this core intact. Yeah. You get your material out intact, so you can study like a full like hydrostratigraphic core or like geological core. You study it like layer by layer and study it in detail. Yeah, but for this, but as he's drilling, he would know that okay, from these depths to this depths, all I was getting was shale. From this depths to this depths, I was just getting sand. Then I was getting shale, and then from this depths to this depths, I was getting shale. Here, from this depths to this depths, I was getting shale, sand, and silt sand. And so when I was like when I was doing this drilling, I was supervising this drilling. So the driller was getting his log. I was also getting my log. So I would say, and if I am uncertain, I will ask him. So that's also something. Like we are not a geologist. I'm not a geologist. Yeah. So the drillers usually they are geologists. Yeah. Or could be geologists. Yeah. So if you are uncertain, ask him. Tell him like, okay, I'm getting this. Is this looks to me like sand? Do you think is this sand? He will tell. And these drillers are very experienced because they are. This is their region. They work in this region. They know it very well. They know the subsurface very well because they have been doing this for years and years, and they're doing this every day. They've been drilling every day, and so they are very well experienced. So if you are uncertain, you can just like tell him, okay, I think this is sand. What do you think? And he will tell you, yes, this is sand, or this is specific type of sand, because they will know, like in this region, they could be different types of sand. So he can tell you, like this is specific type of sand. You see, for example, it has like this slight blue color in it, or it has this slight brown color in it, or this light yellow color in it, or whatever. Yeah, or it has this dark color in it. Yeah, so they will know this very well, and then they will provide you with this information. Yeah, So as the driller was recording his rock, I was also doing my homework and I was also recording, doing the same. Like, at, and the driller will tell you, like, now we are at 1 meter, we are now at 2 meter, we are at 3 meter, we are at 4 meter, and I was recording this. I think every uh, few centimeter I was recording this. Not only I was recording this, I was taking sample. Like, I had like plastic bags and I will take the sample material and just put it and mark it, like with a marker. I'd say this was at like 30 centimeter, this was at 50 centimeter. Why I was taking sample? Because later on maybe geologists will come and look at this sample and have a better understanding of what is in the subsurface. I couldn't, like, as like an engineer, I just have a simple understanding, but a geologist could have a more thorough understanding of these things. Yeah, but that's not what I wanted to tell you here. What I wanted to tell you here is that you can also do like electrical resistivity or other type of borehole survey, yeah, borehole logging, yeah. So the driller, as a bonus, what he did like borehole geophysics for us, and that's a bonus because that's very cheap. Like, this borehole geophysics, it costs like about 100 euro. Like, drilling costs 20,000 euros, this costs about 100 euro, and it's done very quickly. Like, you do it in 10 minutes or something, yeah, or 15 minutes, because basically, like, what you do, like, you have your logger, you drip it in, like, so you put it here, then you do your reading, and then you keep, as it keeps, like, you see it has a cable, you keep dragging it down, down, down. As it moves down, it takes a measurement. And it could take a lot of measurements. So it could not only do resistivity, it could do like resistivity, it could do self potential. And you know what else it does? It does borehole camera. Yeah, borehole camera is just a camera for the borehole, and it's 360-degree camera. So you get like a 360-degree image of the subsurface, as if you go down there and see it. So that borehole camera is also very useful, because you got to see with your own eye, not just with geophysics, you got to see with your own eye what is down there. Yeah, but this geophysics is, it will penetrate deeper. So, like, for example, like resistivity, when you do borehole resistivity, there are two types of borehole resistivity. There is one called like short normal. Short normal might give you like what is happening until here, yeah, with a very high resolution. And then you have like long normal electrical resistivity. Long normal electrical resistivity might show you up till here, like might give you an image of all these like section, but with less resolution. Yeah, and so in addition to the surface geophysics, like what you do in the surface, like this ART, like when you put like this 4 electrode or 48 of them, you can also do borehole geophysics. Yeah. So let me show you this example. Like, so borehole geophysics, like short normal resistivity, this detect fine scale variation, like thin layer near like the borehole, for example. Uh, Long normal resistivity, this can access deeper on the broader formation change. So this can like go deeper, just as I showed you. Self potential, like this is called like SP or self potential. This identifies salt water, like negative deflection due to electrical potential difference between the formation and the borehole. So basically, like you have like your borehole, yeah, and then you have like your formation here, and due to like uh, electric potential differences between like your borehole and your like, let's say you have like your drilling mud here, yeah, so like let's say your drilling mud is here, or like your casing is here, like, so this one you can do even after you put like your casing in. Like, so you put your casing in, like you have your you put your casing in, you have your your, what do you call it, like you have your uh, like your casing and your filling material, yeah, like your filling material, or uh, uh, then there that will create like an electric potential, and based on this electric potential you should be able to identify like different fluids in your formation. Like so, because different fluids they have different ionic concentration. Like salt, for example, has very high ionic concentration, and then it ions like move from higher concentration usually the formation fluid to lower concentration. That would be the mud filters, for example, like your mud filters that would be or your casing, yeah, and your mud filter or your casing. So this movement of ion, this will create an electric potential difference, which is measured by this SP tool, self potential. Negative deflections that would be caused by the flow of ion due to like salinity difference, for example, between the formation water, like higher salinity, and the drilling fluid, like lower salinity. The greater like the salinity difference, the more pronounced it would be this deflection. So that's like self potential. Gamma rays that distinguish between like sand, it has low gamma ray, like low gamma radiation, versus like clay, like it has high gamma ray, high gamma radiation. So that's also another thing. Like like you measure the natural gamma radiation emitted by formation. So clay rich, they are high gamma, they have higher radiation activities and gamma radiation activities, and sand, the sand rich, for example, low gamma radiation formation. So sand generally does not have many radioactive material. It's just sand, it's just silica, versus clay, it has a lot of things in it. Okay, so here this is an example, yeah. Uh, so this is an example for pore hole geophysics. We did this like in Louisiana, in Baton Rouge City, the capital of Louisiana, and we had like about 500 of this pore hole geophysics and logs. And the reason we have we have so many of them there because the Louisiana has a lot of oil production. So there's a lot of oil companies there, and that's what oil companies do. Yeah, they do a lot of these boreholes, and because they need like water for their drilling and for their mining activity, for their oil extraction activities. They use a lot of water, so they understand characterize the water resources very carefully. So here, this is an example of like self potential, and you see all this negative self potential here, like you see this kick here, like this negative self potential here, this negative self potential here, this negative self like potential here. All this will indicate like negative, like saline water. Yeah, so all this will indicate saline water. So if you looked here, exactly as we expected. Yeah, so this would be like a saline water. Yeah, so that's like saline water. So from here you learn about saline water. Now this is resistivity. This is electrical resistivity, pore hole resistivity, and you see all this kick here. So this is clay, low resistivity. This is sand, high resistivity. Then you go here, clay. This is sand, high resistivity. Then clay. Then you get sand here, and then you get sand here, and then you get sand here, clay, and then you get sand here, and then clay. Maybe you get maybe like so. Now this is tricky. Like there is like a certain line above which like you put your threshold above which you can say this is sand or clay. But let's assume like this is kind of like, so this is sand, sand, like we know this is sand. This is unknown, maybe it could be sand or clay. This is sand, and here you see this is sand. This is sand here, and then this is clay. So let's see. So now you hear this is sand. So from resistivity, you will able to know that this layer is a sand layer. And from SP, you will able to know that this sand layer has salt water. Yeah. So you see here, that's basically, see, you will able to know that this is a sand layer and this one has salt water. Uh, and that's exactly like, see, this is our interpretation here. So see, the white is sand, like, so this is sand, this is sand, this is sand, this is sand. Yeah, this is also sand. We interpret this as sand. This is sand, this is sand, this is sand. And you see, this is clay. So this is impervious. Water does not flow here. This is impervious, 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 and this is pervious. So, and so now you see, you got a lot of information, and that's how we will able to characterize the subsurface. we will able to find where are the pervious and impervious layer. And remember, we talked about this when we talked about heterogeneity, hydraulic conductivity heterogeneity, and I told you you need to define like what level of heterogeneity we are interested in. So if we are interested in modeling salt water intrusion in a city like Baton Rouge, what is important is not to understand like the variation of the hydraulic conductivity of different sand. What is more important is to find like, okay, this is sand where water can flow, and this is clay where water does not flow, or impervious where water does not flow. So basically, I need to identify this preferential flow passes, because in this preferential flow passes, that's where we will have salt water intrusion. If our study was, for example, remediation, then we have like smaller sites, then we might want not just to know that this is sand and clay, we want to know like these different types of sand. So, and you can even get this information from here, because like from the shape of this kick, you can different even know different types of sand. Okay, so here this is like one example. This is like here another example. This example, it has a driller's log. Like see here for this borehole, like well name, like the well name EP, like East Baton Rouge 783. We didn't have any driller's log. For this one, we have a driller's log. Yeah. And so this is the driller's log is telling you that this is sand. Yes, we are expecting to get like this as sand here. It's telling you this is sand. Yeah, we are getting sand here. We are getting sand here. We are getting sand here. We are getting all this is sand here. With like a little bit of shale here. Yeah, so this one would be like sand here, and then maybe sand here. Yeah. And this is, so you see like this is the sand, this is the sand, this is the sand, and you see it's kind of consistent with what we are getting also from our driller's log. So here we got like information from our resistivity log. It is consistent with what we are getting from drill log. But which one would be more accurate? The resistivity log would be more accurate, because here there could be like human mistakes. You don't know who's drilling this. Some company are more rigorous than other companies. Some geologists are more skilled and experienced than other geologists. So this one would be like the more accurate generally than this one. Yeah. So information from here would be more accurate than information from here, generally speaking. Yeah. This is gamma potential, and you got like the same story. Remember, like shale has a high gamma activity, which you see here. Sand has a low gamma activity, which you see here. Okay. So if we did this interpretation again, like we got like sand here, we got sand here, we got sand here, sand here, and sand here. How we are doing in time? Okay. Uh, so again, this is like another example. Like, so we looked here in this example at SP, we looked here in this example as gamma and like driller's log. In this example, this is just like SP and resistivity. So from this resistivity, we know that we have like sand here, maybe some sand here, and maybe with some salinity also. We have like some sand here. This one, maybe there is like sand here, maybe there's sand here, there is like sand here, and then we have some sand here, and then we have some sand here. So let's see how we interpreted this. Yeah, so we got it like we got like sand here. See, we didn't get this one. We got like sand here. See, we didn't get this one. Again, like you have like usually like you do this with a computer program, and in this computer program you define like the salinity level. Yeah, so you digitize these things, and this you define like if you got like less than 100, for example, or less than 20 ohm meters, and you define this as clay. And so this is sand, this is sand, and this is sand. Yeah. Okay. Uh, so I think that's so what did we do with this data? So I told you I have about 500 of these one. So we got like these 500, like we interpreted them, and then we used some geostatistical method, and from this geostatistical method we will able to create this image of the subsurface. This is just one image, because we also account for the uncertainty. So you can get like hundreds of these images, and then there are methods for accounting for this uncertainty and translating like propagating this uncertainty to your flow model and propagating this to your final answer. So like your final answer will not just be one number, but would be like a range, yeah, and would be like a probability. Yeah, and that's more rigorous than just having, oh, this is the correct answer. So we don't say, oh, this is the correct answer, but we give like a probability distribution with the mean and the standard deviation or something like this, or like a credible interval or whatever. Yeah, not just like a mean value, but like ranges of possible outcomes as well. So here, like you see, these are the different sand units. So like you see here, these are the different sand unit, and the blank one are the clay. And these are basically the preferential flow passes where salt water intrusion will occur. And these are different aquifer units. They are named by their depths and they are used like, so for example, I told you about like these oil company generally like use water from like these two aquifer, municipal water use. So this is called like the industrial aquifer, and this is the municipal aquifer, like the 1200 foot sand, 1500 foot sand, 1700 foot sand. They are named by their depth from the subsurface. So that's the name of this unit, like 1500 foot sand, 1700 foot sand, 1200 foot sand. Okay. And these are some important well in this region. And if you want to read more about this, you can, I think, you can check if you want to see more details and about this characterization, you can just download, like go here, download this paper, and you will find more details about this, about like this borehole logs and how, yeah, I already showed you this, but you can see also the geostatistical method and what did we learn from this study. Like for example, one thing we learned from this study, like let me show. See, you will be able to identify like preferential flow passes. We know that saltwater intrusion is occurring across this fault, and you see here like water, like saline water will come here, it will contaminate this one, it will contaminate this well, it will contaminate this well, and in the future it will contaminate this well, something like this. So you can also plot this here. You see, just from a very narrow, see, that's what exactly I was telling you, just very narrow preferential flow path. See here, like this white is sand, like where water flow. Like so, the gray color, this is clay where water does not flow, and the white is sand. So you see, like water just flow here, and it will go and contaminate this one. So we're able to plot uh, preferential flow passes and show how this guy got contaminated. For example, with saline water or good saline, yeah, how we salinize it this one, and you can see it here. Okay, so that's like what you get from these type of analysis. Okay, I think this video is getting very long. Uh, this is electrical resistivity imaging in the field. So let's just watch this video together, yeah? Because we like what we learned now is what is electrical resistivity imaging, and what we also learned is why this is important or what we can use this for. In this video, we will like learn how to do it, how to actually do it. So let's just
Fall into savings at Tire Choice Auto Service.
let's
Island's field video on Welcome to the University of Rhode Island's field video on ERT or electrical resistivity tomography. This is a geophysical technique we can use to scan the invisible, meaning we can see underground. It helps us map lithology, groundwater, and areas of high or low conductivity, such as saltwater intrusion and water table delineation. In this project, it is mainly used to identify saltwater and freshwater mixing zones underground, which helps us map areas of saltwater intrusion. When choosing a survey site, there's a few things to keep in mind. We have to be away from the roadway, power lines, and not interfere with foot traffic. ERT requires a long extension cord-like cable that should be kept as straight as possible during a survey, so our site needs to cover a large area of uninterrupted space. So, for the main equipment we will need for a survey, at least two 12-volt deep cycle marine batteries, the ERT setup including Super Sting machine, a box of 56 electrodes and connectors, the main cables and connectors that come with the Super Sting, and cat litter. Be sure to bring other things like water, food, buckets, a canopy for sun protection, and a laptop for downloading data later on. Safety is important at any field site. Don't forget gloves, long pants, closed-toed shoes, and a safety vest. Now that we're ready and have a site selected, we can begin measuring our land. Depending on your site, you must determine how far apart the electrode spacing should be. They are spaced at 5 meters directly on the cable, but you can do less depending on the length of your site. Once this is determined, the electrode should be placed at each interval, and our cable
So here is, remember, they said like they place them at 5 meter intervals. That's because they want to go like deep. And if you want to go deeper, you place them at a larger interval. For the equipment we have here, we because mainly many of the aquifers that we are interested in here in this region are like at shallow depth. So we got our instruments that are placed like the interval we have for the instrument, which we will do in the field trip is like 2 meter apart. So the electrode are placed 2 meter apart, but you can place them any way you like. You can place them 1 meter apart by just coiling them around. Yeah. So I just want to tell you this.
is unrolled along the parallel. Consult your SuperSting manual on which end of the cable is male or female. It's important to know before unraveling, as the ends need to be compatible when connecting to the machine. Now that our electrodes are placed, it's time to make them stationary and connect them to the cable. When digging holes to place electrodes in, depending on your site, you may need to add salt water and cat litter. Cat litter has a high clay content that holds moisture and enforces connection of electrodes. Mix cat litter with salt water in a bucket for a paste-like formula to add in the holes for electrodes. Be sure to make the holes narrow and deep for better contact with the earth. We then hammer the electrodes into the ground so that only about an inch sticks out, just enough to see the connector. If contact resistivity issues persist later on, it can typically be solved through the addition of more cat litter and salt water. Again, use your SuperSting manual for specific instructions on how to run the test. We typically use the Winner-Schlumberger test for our purposes. This test runs approximately 100 minutes, but can be faster depending on how quickly the electrical current passes into the earth. Someone should be monitoring the test during this time to make sure it doesn't encounter any errors. These errors can include a full memory or low battery voltage. Data can be collected directly from the SuperSting or downloaded at a later date. If you are running multiple tests in a day, downloading data on site can ensure the memory won't fill up and you can have a quick look at your data. So, how does it work? Electrical current is injected to the earth by a pair of electrodes. We call them current electrodes, and the voltage difference is measured by another pair of electrodes. We call them potential electrodes. This process works like injecting and pumping using a set of tube wells. Knowing how much current was injected and the voltage, we can calculate the material resistance using a basic Ohm's law.
These measured resistivity points go through an inversion process to obtain the resistivity distribution on the subsurface. There are several computer programs for the inversion, such as Res2D-Inf, Earth Imager, Simpeg, ResiPi, and others. Here, we see a resistivity profile from a barrier island in Rhode Island. The red color is a brackish water, the light blue is fresh water, and the light green is the mixing zone of fresh and brackish water. The dark purple layer on the top is the unsaturated zone, which is above the water table. Taking data from the same site over multiple years can give us a good idea of how the hydrology of an area can change over time.
Geology of coastal aquifers is not homogeneous. Taking samples to bring to the lab and measure its hydrogeological characteristics allow us to correct what we saw from the ERT data and make assumptions about lithology. Here, we are taking samples from several locations along the South Kingstown town beach where we did an ERT survey. ERT surveys give us bulk resistivity. Taking samples and finding aquifer properties can correct our image to fluid resistivity. These samples are taken into the lab, measured in columns with some sort of bucket to catch water. We pour water in the top of the sample columns until it is fully saturated and simulate its natural state as an aquifer, which would be compacted. Once in its natural state, we test for porosity, specific yield, and specific retention. As mentioned, our surveys measure bulk resistivity. If we have a well in a survey location, we can get what is called ground control, which validates our ERT data with point data of the water level and electrical conductivity from a well. Using an EC meter, we monitor a well every half meter, collecting electrical conductivity and temperature. This is typically done every 2 weeks and gives us a baseline of the water table to compare to. Now that you're ready, good luck, and we hope you enjoy the fieldwork.
Okay, so this give you like a quick overview on how to do this. And again, like what you do and like all the other measurements that you take, that will depend on the purpose of your study. Yeah, so there here they were like collecting like electrical conductivity data, because this electrical conductivity data will validate their salinity images that they are getting from their ERT. Yeah. Uh, they will like also taking some sample, like some sample, and measuring them in the lab, like for specific retention and porosity, and also to look at we do here something similar. So we do like when we do electrical resistivity tomography, we don't take sample to the lab, but we measure to just do this validation and to better align our imaging with what we have in the field. We measure we measure uh, hydraulic conductivity value using our permeameter. So we use our permeameter to measure hydraulic conductivity value, and then that will give us a better understanding of okay, so here we have this hydraulic conductivity value, and in this region, and this is we are getting this like electrical resistivity value. So we can put some we can correlate these two together, and that's basically what you will be doing in next lessons. That's what we're going to do in next lesson. We're going to do like a hydraulic conductivity value from not from a permeameter but from a pumping test, and we will overlay them with electrical resistivity value measurements, and we will do this to characterize the subsurface, to find like to create like the hydraulic conductivity field, and have like a rough understanding of different hydraulic conductivity values. Yeah. For different zones in our field. Okay, so I will like end up with this. This is just like a simple exercise, and this simple exercise will just like help you to do your homework. So these are like a resistivity value. Yeah, like you see them here, and like you see them here, and like check the notes. Like in the notes, I will put like the source, for example, where I got this from. So check the notes, and then you can find more information here if you want to read more. So these are different resistivity value. We are expecting that the subsurface will have like sand and clay. And I'm telling you where are the sand and where are the clay layers. So like, is this like a clay or a sand layer? Is this a clay or a sand layer? And you see here, this is like long normal and short normal. So we usually like when you go do this borehole geophysics, you do both of them. You do short normal and long normal at the same time. Yeah, you get this. And SP and gamma ray, you all get this like data, and porthole camera, as I mentioned. So just based on what we learn, what do you think? So I think like based on what we learn, like I see a sand kick here, I see a sand kick here. So that would be like clay, that would be like sand, that would be clay, that would be sand, and that would be clay. That would be my interpretation for this. We have a clay layer, sand layer, and clay layer. And you see here, let's look even at this one. Yeah, see the sand and gravel. uh, they have this like range of like resistivity here, and then the clay they have uh, this like range of resistivity here, can goes up to 100 meter. Remember 100, see remember I was telling you this, you need to put this cut off like where like, because see the clay could go up to 100 meter, and you need to put this cut off, like would you put it like at 100 like 100 or 20 or 40 or something, and then the computer program, you just tell him okay, anything above like 50 meter, like consider this like sand. Yeah, don't consider it clay. Like 50 ohm meter, sorry, not 50 meter. Yeah. So this will be like, let's do this. Yeah, this is clay, this is sand, this is clay, this is sand. Now let me tell you something. Yeah. If this was saline water, now you see here, now that could also get confusing. Like if this was saline water, salty water or saline water, not fresh water, then you will still get this kick, but they will not be so pronounced. Like let's say the resistivity of sand and gravel is here. If you add saline water to them, they will move to here. Yeah. So you will still get this kick. So like if this was saline water, it would look something like this. It would be like something like this, but then you will have a small kick here and then something like this and then maybe small kick here and then something like this. And that's how you, okay, so this is like fresh water, sand, and that would be like salt, line, water, sand. Yeah. So that would be like fresh water, and that would be saline water. Okay. So that's basically that's. I mean, again, like we. This is just like short introduction so you become familiar with this. If you want to use any of these methods, you have to study it and learn it in details. And it's not difficult, yeah. It's like, for example, like our ERT equipment, you can just read the manual in one day or something and learn how to do it in one day, and then watch like this half-day tutorial, and that's it, yeah. And then you will find like hands-on experience, yeah. But we cannot cover this like in this short amount of time. But I give you these resources and if you want to, and I give you the resources, but more important than the resources, I give you the basic concept. So the basic concept is this is what you basically should understand here. You should understand, like, be able to identify like pervious and impervious area if you got like these data. Yeah. And if you got an ERT, electrical resistivity data, you should be able, by different resistivity value, you should be able to do like different interpretation. Okay, this is sand, this is clay, this is that. Yeah. If you are uh, doing like this to investigate cars, for example, like cars feature, you need to read about cars feature and ERT in cars feature and get some example. Like before you go to the field, that's what I did in Ireland. Like I didn't go to the field and just did this ERT without like, I got some sources about like ERT and karst and how to interpret, because each of these rock, the interpretation would be different, and then there would be like a lot of heuristic and a lot of knowledge that you need to gain. And then once I gained this knowledge, then I was able to interpret like these images that we got and said, oh, okay, here's maybe a cave, this is maybe a karst conduit, something like this. Okay, so I think that's all for this lesson, and I will like see you in the next lesson. Yeah. And the next lesson, we will see how to use this electrical resistivity data and pumping test data to create a hydraulic conductivity field conceptual model, which we will use for our groundwater modeling. Okay, so see you in next video.